Hello everyone, this is KV7006 Machine Learning. Today's video is about the Principal Component Analysis, or called PCA. So in another video, I have recorded about LDA. Just very briefly recap that. So the previous video gave us some idea why we need the dimension reductions, and we have seen some samples. So this is two-dimensional data. So we put the x-axis and the y-axis in different location to the dataset. We generate different results. So one way is doing that, another way is doing that, another way is doing that. So you can see the dataset and the x-axis have different relationship or location. And in a technical word, it's called projection. We project data onto different axes. Okay, so now what is the principal components analysis? So here we want to identify most important component in the dataset. Imagine I got 10 features of the dataset in the data, which represent 10 different measures or features of the data. However, we don't need all these 10 features all the time. We probably only take first 3 or 5, which can preserve the information in the original data. However, the size of the data will reduce. Imagine we got 100 records, we got 110 features or components. So in total, we have 1,000 data points. If we only take the first 5 most important features or components, my dataset only 500, which is reduced half, 50% of my dataset. This is especially very important if we are processing image, we are processing video. Especially in IoT scenario, we transmit the video through internet to the data center or management center, which normally take a huge amount of volume of data. So if we could only use a less number of data, probably we can make a decision much quicker. So you could think in somehow principal component analysis is kind of way to compress data, but preserve meaningful information we need. Okay, that is what it's about. So how can we achieve that? Our approach is to find projection, capture maximum variant directions. So in the previous video, we have seen we can change the location of axes to locate to different location related to the data. So this purpose is to find out the maximum variance. So we change different our x-axis, y-axis, and then find the way to represent the data. So that is aim, that is the approach, and how we calculate that, and how we actually process that. So the first component, principal component, normally is direction with the highest variability. The second one would be the next highest variability, normally in 90-degree relationship to the first component. And the following principal components will have less variability in a descending order. And then end of the day, you got a list of the component with a descending order of the variability. To the highest priority, which means in some way more important, and so on. So every component are in 90 degree to each other. So in many applications, you could determine number of K. How to determine K is another research topic area. Normally depend on the application domain, expert knowledge regarding to the data, and also for real-world usage purpose. So you set up some threshold in terms of value of variability, and you determine a number of K. So given number of samples, each sample has d dimension is a real value. So principal component analysis is not reduce the number of samples, let's here K. Instead, it reduces the component or features, or what you use in database is the variable or which describe the dataset. So imagine you got a dataset which has each row is a record, and which column represent each features or variable. So these features or dimension describe the data. For example, describe the depth of image, color, or etc. So principal component analysis is not to reduce number of n samples. Instead, use less number of variable to represent the same dataset. So the approach is to project data from D dimension to K dimension. K must be less than D. So we need to calculate the maximum possible variance in the project data. How are we going to that? Okay. First, we set off a component, a list, which is U. So original one we have D, 1, 2, 3, 4, 5 until D. D is originally dimension to be the component. And then, as we said, each other is in 90 degree to each other. So each principal component is a vector of D times 1. And we want to only keep the first principal component with the highest variability. So we need to project a data point, or a data point is, let's say, is a noun. For example, U1. U1 is first principal component, which is on this original dataset. So you can see this one, U1. We need to calculate the means of this one as well. So this is X bar, which is the mean of the Xn. So we know how this can be calculated mean. The variance is the projected data on non-project direction. So this is example of how first component, principal component are calculated. So we are going to use that variant formulation to do the calculation. And then we have a covariant matrix, which we can define as below. So this function, covariant matrix formula, is very common in statistics. So Xn and this is the mean. So they are related in 90 degrees. So this is X is the variant matrix we need to calculate. So if we think one component is a first principal component, it must maximize the project data variance. So if you have other component, for example, you have U2, U3, which have a higher variance than U1, and then that one will become most important principal component, or the first principal component. And also we introduce a multiplier. You can consider is constraint, is a weight for this constraint. This is object function. So now we add a multiplier, and then we do a derivation subject to U1, and if we set them 0, this will simplify like that. So now we got a result of eigenvalue equation. So the first principal component must be an eigenvector value of X. So if we have several eigenvector of S, which one is U1? U1 is the most important one. So consider this formula. If we set this constraint equivalent to 1, so the relationship is the 90 degree. So equivalent, this is a constraint we defined previously. So number 1 should be the last eigenvalue, because U1 will be the maximize the value of the variant. And then U1 will be the first eigenvector of X. So X is a covariant matrix. So U1 will represent the first one. So just remind you, S is covariant matrix. So U1 will be the highest eigenvector of X. So the first principal component, once defined, we know the direction of the highest variance of data. Then following principal component can be given the less important value of eigenvector of S. So this is about the calculation. Now we look at the algorithm itself. Step 1. To calculate the mean of data, straightforward, and use the previous mentioned covariant matrix to generate S. So we have seen this before. And decompose the eigenvalue to D times T matrix, and choose the top K eigenvector, each corresponding to top K eigenvalue. So now we got a list of components U1 until UK. The multiplier will be in a descending order. The first one will be more important, and then second one, and then finally number of K. So U becomes a projection matrix, represent the with size of D times K now. So you can see original we have D times C, now we have D times K. So we project each sample and then we calculate their equivalent to U and Xn. So Kn will become embedding of the Xn is a K vector size of k times 1 vector. So we will see an image representation. So imagine I have only one sample. Let's say original dataset here in blue. I have D dimension, D component. Now I want this one become, how to say, K dimension. So we have a projection matrix here. We times up with original data, we generate that. So you can see actually if we only preserve, let's say this is the original data, we find out the principal component K, okay, and then we also know U, the projection matrix, okay, and you can see if we have the compressed data and also projection matrix, we can reproduce the original data. So this can be seen larger data samples. You can see the size of sample remains the same. My projected unit have nothing to do with number of samples, so they remain more or less unchanged. So it's irrelevant to number of samples. Okay, and then we could use Z is what we generate here, calculate by this formula, okay, and represent the original dataset given the knowledge of projection matrix. So this is especially important or very useful for image analysis. As you know, images are multidimensional and normally preserve some data which probably irrelevant to face recognition, for example. Although we have a lot of dimension, you will realize that if we want to identify this person, recognize this person, we normally need probably less dimension to recognize the same person, especially in video. If we can use less number of dimension, would be much better. So we could call this is reconstruction. We can reconstruct original data, not exactly, but somehow. So you can see this U projection matrix more or less remain unchanged. And then we use less number of dimension. We all have original size of the data sample. We can use this projection matrix times less dimension and reproduce original data set. So this one way of compressing data, as we see here before, and also we can reconstruct original data by reuse the U and the Z. To summarize the dimension reduction, so some dimension reduction with label information, with class information, which is help us to do classification. For example, your image has person, female or male. For example, you have a class label. For the principal components analysis, we ignore label information. We only want to try to find the maximum variance, the direction of that, and generate the U projection matrix. In the last video, we already load the linear one, LDA. They could also take count of label information. This LDA normally preserve classification put together of the same class and then by projection. So if they are not same classes, they could place further apart. So just to remind you that we, in this principal components analysis, we are not used label information. So that more or less is the dimension reduction. In summary, we have learned PCA today, and in another video, we already learned the linear discriminant analysis. Okay, so that is for this week. Thank you very much.